I'd like to start by thanking the organisers for inviting me to present at this session. And I'm going to give a talk entitled Ultra-Low Power Epidermal Embedded Communication Platforms for Heart Rate Monitoring. The talk's given by myself, Professor John Batchelor, and it's mainly based on the work of my colleague, Dr. Robert Horne. So the contents of the presentation, well, I'll start off by telling you some of the recent work that's been done in my group at the University of Kent and with our collaborators. And then I'll mainly be talking about the BodySense project and the platform that we're creating for a tag system capable of streaming accelerometry data and much more recently ECG measurement. And I'll end the talk by talking about the next developments. So at the University of Kent, we're in the city of Canterbury in the southeast of England. The group that I supervise, the two academics, myself and Robert Horne, and then some postdocs and PhD students who will have done some of the work that I'm presenting here. So we have a fairly long track record of working with on-body communications and specifically on-skin communications at Kent. So a few examples shown on the screen there, where we started on the right, developing wearable antennas which could be integrated with clothing. So metallic antennas that looked like jeans buttons or like belt buckles for trousers. And then we have developed temporary tattoo transfer antennas, and these were aimed at RFID tagging, and a variation of the on-skin tattoo is shown for an in-mouth design, shown in my own mouth here on the tongue, whereas in fact we actually use the tag in the end on the roof of the mouth on the hard palate, and this was used as a tongue proximity sensor as a human-computer interface. So just looking at some specific examples of recent work which builds towards the work I'm going to mainly talk about. Some recent work we've done, this is with our colleagues at the University of Manchester, using the temporary tattoo transfers that I mentioned. These are printed with silver ink by inkjet. And the photograph shows three types of electrode that were compared. The large white electrodes are standard clinical, and these use a wet electrolyte gel. The middle electrodes are etched copper on a polymer sheet, and the electrodes on the right are temporary tattoo transfer electrodes. And so these three electrodes were compared over a long period of time, over a 5-day period, and the test subject followed usual physical activities, including exercise and running, together with showering and so on. And the ECG measurement was taken on the subject's chest periodically over the week. And the traces shown basically compare the standard clinical electrodes, which is the blue trace, with obviously the benchmark high quality signal. The green rather noisy signal is the copper etched electrodes on a polymer, where it has quite a poor signal to noise ratio. But the tattoo electrodes, the printed silver tattoo electrodes, they actually give quite a good performance, not quite to the clinical standard, but a pretty good performance considering they're a cheap and long-term wearable type of electrode. So there's an example of some work we've done with our colleagues at Manchester. Other recent work, trying to reduce the size of our temporary tattoo transfers. So here's an antenna. It's essentially a dipole shown meandered and folded round. So in this case, we reduce the antenna diameter to 3 centimeters and get good read ranges comparable with the larger tattoo antenna that we originally developed. So we can get read ranges of over 1 meter with a reduced size antenna. And in fact, that antenna design was developed further so that it could fit on a silicone prosthesis, which is used with people who have had tracheotomy surgery. So after throat cancer, when part of the tracheotomy is removed, there is a skin stoma, a surgical hole in the throat, through which this prosthetic is, this prosthesis is inserted, and the antenna can be basically mounted on one of the faces of the prosthesis. Now, the reason for this is because these inserts are very prone, these implants are very prone to fungal infection. When fungal cells colonize an implant, they start to form what's known as a biofilm. And the mechanical properties of the biofilm, I mean, apart from causing infection problems in the patient, stop the prosthesis valve working properly, and therefore an intervention is required, which is not only an unnecessary trauma to the patient, but is expensive clinically. And so monitoring the onset of the infection is highly desirable. And in this case, we simply use the formation of a biofilm over the antenna surface to detune the antenna slightly and pick up a change in the reflected signal from the patient. So this is work that was published in 2019. And another example of the sort of work we've been doing, in this case, not necessarily for on skin, but here we have an elastomer-based antenna where the antenna itself, in this case a dipole, has been bonded to the elastomer at specific points. And as the elastomer relaxes, the dipole is basically buckles and changes its resonant frequency as a result. And in this case, we exploit the fact that the elastomer swells as it's exposed to a solvent vapor. And therefore, in this case, we can simply detect the presence of a solvent vapor around the sensor. And again, this is done by a detune in the frequency of the reflected signal. So that's some of the previous work that we've been doing, all of it based on low energy RFID-based sensing. Now, in case anyone's not familiar with RFID, we work in the UHF band, which in Europe is centered around about 868 megahertz. Effectively, it's similar to the sort of air traffic control transponder radar systems which identify aircraft. The tag itself is a simple printed antenna with a single transponder chip on it. And that transponder is energized by the read signal that comes from a remote read system. And when the chip is energized, it effectively generates, through switching at the antenna terminals, it generates an ASK modulated backscattered signal, which the reader picks up either with a monostatic antenna or a bistatic arrangement. So the system itself is quite simple, and in the fundamental sense, it doesn't require any battery at the tag. It's entirely based on received energy and a modulated backscatter. And providing the channel is relatively unobstructed and we don't get polarization or mounting losses, then the ranges of several meters are quite readily achieved. Certainly sort of 7 to 10 meters can be achieved without too much trouble if the environment is not problematic. So to focus on the BodySense proposal, so this is the project that is developing the sensing platform that I'm going to talk about for the rest of this presentation. There's a simple roadmap shown on the screen, and this was developed in collaboration with our partners at the University of Manchester and at the High Value Manufacturing Catapult in the UK, CPI, who are helping with the scale up of the platforms that we develop. So starting off with the idea that we will develop a test platform using off-the-shelf components and swap those components out with printable alternatives and aim for flexible skin mountable technologies, which eventually will be batch scaled and then continuous roll-to-roll processed. So the requirements of the BodySense skin patch, well, we're aiming, our target measurement is ECG. We are going to use passive UHF RFID as the communications link, but we'll have a battery assist on the tag to power the tag processor electronics, and in order also to sensitize the RFID process slightly and to improve the modulation depth of the backscatter. But the link remains a passive UHF link. The ECG signal requires 200 Hertz sample rate. With a high data integrity, we need a bit error rate of less than 0.1%. And the read range we're aiming for from a direct on-skin mounted patch is at least 1.5 meters. So for use in sort of semi-clinical or maybe domestic settings for reasonably small-sized rooms. Now, RFID communications, well, of course, it's originally designed for things like asset tracking, where we are communicating with a large number, a very big population of tags, but sending very small bursts of information, essentially just tag identities. And fundamentally, the system isn't really designed for live streaming large amounts of data. This means that most of the tag transponders available are certainly not really suited for live streaming. But there are a few types of transponder which do at least, and in fact increasingly so, allow things like computer bus access, so SPI or I2C bus interfaces between a transponder and a controlling microcontroller. To be useful, the RFID has to, of course, follow the regulation, which is the EPC Gen 2 protocol for RFID. So the system we propose follows that regulation. And we're using a bespoke reader control software. So we're using the API available for the reader that we use. So we've programmed our own control software. The reader we use is the ThingMagic M6E, using its Mercury API to derive the software. So the system block diagram, so the top part of the diagram is the tag. So we have the chip transponder we've chosen is the EM4325, controlled by an MSP 430 microcontroller, Texas Instrument microcontroller. And the ECG data is taken using a MAX 30003 chip. And then there's the battery assist LiPo battery. In fact, not shown here, there's also an accelerometer, which is on the tag as well. Now, the link back to the reader, the remote reader, is over the 868 European UHF RFID band to the M6E ThingMagic reader, and then there is a desktop computer controlling the reader using the API. So as I mentioned, we're using the EM4325 RFID transponder chip, and this was a consequence of needing to stream the data. In order to stream the ECG, we wanted 0.8 kilobits per second, and the memory has to withstand the continual addressing and writing that's required for streaming data. Now, unfortunately, most RFID transponders that I mentioned are developed just for bursty, occasional communication. And this means that the memory they use tends to be EEPROM, which is slow to address, and it also has a limited write life cycle. So usually the memory will fail if it's EEPROM after about 10,000 writes, and the speed of address is about 50 bytes per second. So the speed is too slow, and ordinary EEPROM memory would fail relatively quickly if we tried to stream data over it. Now, the 4325 chip offers something quite unique, which is the ability for the user to address RAM in its memory, which is much more appropriate for a real-time system or streaming data. So this is the reason really why we selected this chip, because of its availability of user RAM. It also provides a battery-assisted mode operation, which is important for us because we have to drive the microprocessor. And it also improves the read range, which is a big challenge for a skin-mounted tag. So the types of memory available in the 4325 transponder, there's the EPC, the electronic product code memory, which is the EEPROM. There's user memory, which is also EEPROM, and then there's a register available in the user memory, which is RAM. The EPC, which is the most usually addressed part of the memory, this is where the essentially the identifying information for the product that is being tagged is held. So this is, of course, not usually expected to be rapidly rewritten. and therefore it's not only relatively small, but it's slow to address and would fail if it was constantly rewritten. Whereas the user memory EEPROM, of course, suffers the same problem. It's bigger, but it still has slow access time and would fail. And then there's the user registry RAM, and this, of course, being RAM is volatile, which isn't a problem for streaming data, but it does require a more complex addressing from the reader. And in fact, this complexity will reduce the read range. In fact, it'll roughly halve the read range, which is why the battery assist is very useful to improve the read range over its reduced level. Just looking at the memory table of the chip, this is showing the system user data, and the registry that we use is highlighted here. So this is 2 8-byte pages in the user register. It's RAM, not EEPROM, which gives us sufficient space for these two, with these 2 8-byte pages, gives us sufficient space for transferring ECG data into packets. And in fact, it also leaves room for sending error correction as well. Now, of course, if we are going to stream data, it has to be packetized. So the screen here shows the data packet actually for the first version of the platform, which was just accelerometry. And so typically for a packet, obviously we start with a frame number, we've got the data payload, which in this case is XYZ accelerometry data, and then there is some error correction at the end, a cyclic redundancy code in this case. So that's the basic form of the data packets we're sending. Now, because it's a streaming system, which is essentially it's a real-time operating system, this means that we have to avoid clashes or contention in the system. And therefore we use interrupts-driven blocking basically to prevent the microcontroller from trying to address the RFID chip at the same time as the ECG data is being written from the ECG chip. And also we have to make sure that we don't try and transmit or talk to the RFID transponder at the same time it's being interrogated by the reader. So there has to be interrupt blocking to stop the data being lost when we get clashes. So we can just follow the data pathway in this case to see what happens from basically from the ECG data which is being gathered on the user in question. And then there's a remote PC which is driving the reader. So if we follow the data path with the application running on the PC, which will request the RFID reader to interrogate the tag over the RFID link, so that the tag on the user's body receives an interrogation from the reader. And in that case, the RFID transponder will send an interrupt to the microcontroller unit to inform it that it is being interrogated and it mustn't have data sent to it by the tag. Now, in the meantime, the ECG chip is streaming data, so it'll fill up its onboard buffer. And when that memory register is full, the ECG chip generates its own interrupt for the MCU. To inform the MCU, it must download the data in the buffer from the ECG chip. That data is formatted in the microcontroller, so it's ready for packetization. And then the microcontroller will wait until the interrogation flag from the transponder goes low. So when that occurs, we know that the transponder is ready to transmit data back to the reader. And so the MCU writes the data packet into the user registry of the transponder chip, and that is sent via the RFID link to the reader. And therefore the RFID ECG data is reassembled at the PC, and the cycle is able to continue or restart. Now, in order to fabricate the prototype tags, colleagues at the University of Kent in the Material Science Department developed a printable battery. So this is formulated into a 15 milliamp per hour battery giving 3.7 volts. And this is sufficient to power the MCU power draw, which is less than 2 milliwatts. The developed prototypes are shown here. So here's the first prototype before the ECG was added. So this is an accelerometry version. So the first test circuit is on rigid FR4. It's using an off-the-shelf LiPo battery. And then the second version here is an equivalent design, but it's on a flexible Kapton substrate. And it's using the thin film printed battery developed at the University of Kent. The antenna in this case is just a simple dipole. Then the following version, so this is the version incorporating the ECG. This is again a rigid FR4 test circuit with the various components indicated for you, and now the dipole antenna is being converted into a perimeter loop antenna. Then we've got the flexible Kapton prototype shown here. It's an exactly equivalent circuit, but it's now on a flexible substrate. And the printable battery is mounted on the rear, and its size is sufficiently small that it doesn't interfere with the perimeter antenna. Okay, so the measured data packet transit time is shown on this slide. Effectively, the cycle in its usual form should take 3 milliseconds, and we can see that the red baseline establishes most packets do indeed take 3 milliseconds to arrive at the reader. But there's a significant number of packets which are taking 6 milliseconds, or some of them taking even longer. So if we take the 3 milliseconds as the minimum packet transit time, which corresponds to about 5 kilobytes per second, the 6 millisecond packets are essentially taking 2 cycles to arrive. And this is caused either by blocking at the tag end to avoid clashes and data loss, or it's caused by interference on the RFID link, meaning that packets take longer to arrive and need to be resent. The very long transit time shown in the center of the slide, this is basically following the regulation required by the ECG RFID regulation. So this is saying that you can't continuously transmit at the RFID band for more than 4 seconds. So every 4 seconds or so, the system closes down and takes 14 milliseconds to recover. So a packet transmitted at that time will take the full recovery time before it arrives. So in order to try and improve that, the average packet transit time, we introduce some redundancy to the packets. So the packet structure shown at the top left is the original packet structure, where we have a header with the frame number, we have the data payload for 6 bytes, then there is an unused 4 bytes of empty data, and then there's the error correction taking 4 bytes at the tail. And so we can add redundancy to that in order to improve our transit time. So we now have 2 data payloads in the packet, both of them 6 bytes to fit within the total 16 bytes. And that means we have to reduce the error correction at the tail of the packet to just 2 bytes. Now the 2 data payloads, the first payload we can regard as this cycle's data, and the second payload is the previous cycle's data, which is being resent. So every payload gets sent twice, and that redundancy prevents almost always the need to use 2 cycles to send data. And you can see here from the measurements that the number of packets taking 6 milliseconds to arrive has been considerably reduced. Those remaining longer transit times we anticipate are caused by the remaining blocking, which is instigated at the tag to avoid memory loss or data loss. So now with this system, the average data speed has increased significantly, and it is now arriving at the sort of expected 5 kilobytes per second. So the test for the actual ECG signal itself, so the test circuit was mounted on a user's or a volunteer's chest. In this case, we used clinical electrodes, so this is using a wet electrolyte gel for the first test, and relatively short leads, so the electrodes were not placed far apart from each other. So the slide here, it shows the recovered data over the RFID link, and it can be seen that it's actually quite a good quality signal. The features that I observed in ECG, the PQ-RST features, are readily observable. The signal-to-noise ratio is very good. And in fact, there was no need for any processing on this signal. This is as received, so there was no averaging, no smoothing, and no need to remove mains interference, 50 or 60 hertz, which often requires notch filtering. The sample rate is higher than is needed as well. So we required a 200 hertz sample rate, which is about 0.8 of a kilobyte per second. And we have around 5 kilobytes available. So that's plenty of extra room for incorporating accelerometer data, which will be very important if we attempt to measure ECG over subjects who are moving, because the motion artifacts will appear on the ECG signal. And so the accelerometer data can be used to remove those motion artifacts and restore the ECG signal. Now, the power consumption measured for the system, it came out at with a current draw of 950 microamps for just under 2 volt supply, which is just under 2 milliwatts. So this is while it's streaming the data, and there is no microcontroller sleep mode enabled. So this is running at its on optimized power efficiency. So we're running at less than 2 milliwatts. It's a little higher than we anticipated. We were expecting a draw of just under 1.5 milliwatts, and it's assumed that that extra loss has occurred basically because of the regulator used on the tag. And we can continue to look at this, but we're still actually within a quite a low power limit in this case. And if we were to use a 120 milliamp hour battery, a typical coin cell type battery, that would give us 120 hours of continuous use without needing to use sleep or any recharge on the tag at all. Now, the next stage for the project is to consider the scale up. This is essentially a printable electronics project. So we will move from the etched test circuit on Kapton to a printed version on PET, flexible substrate. And then that will immediately be trialed for scale up for batches of 10 to 15 on a sheet by sheet process. And then moving that on to a continuous roll to roll process, which is available at our collaborators' CPI. And then finally, just to consider the future architecture of our system. And this is considering that if these systems are used widely, then we would need to share the bandwidth rather better than we're using for the raw data at the moment. And so the idea is to consider adding machine learning to the tags to do a lot more processing on the tag itself, and therefore we can send higher level data rather than requiring to send the raw data stream back to the reader. So if we can just send information back about the quality of a user's heart rate, for instance, or heart waveform, rather than needing to send the waveform itself, we can share the available channel much more efficiently with other users. And also, of course, because this is personal data, we need plenty of room for encryption as well for user privacy. So finally, just to summarize, we've achieved 5 kilobytes data streaming using a BAP assisted UHF RFID system. We managed to achieve this data rate by using RAM in the tag transponder rather than the usual EEPROM. We used blocking to avoid clashes and data loss at the transponder. And redundancy in the packets allowed us to improve the transit rate quite effectively and achieve the 5 kilobytes per second. Tag power draw is less than 2 milliwatts, giving us in excess of 100 hours of operation using the coin cell. We've incorporated printable and flexible batteries, which have been developed at the University of Kent. And we're about to embark on a scale-up process for batch and roll-to-roll this is just currently under development and will be presented at a later date. So thank you very much.